Well, good afternoon. I have a hard job here this afternoon, so you may have to help me because I'd like to make it interesting and fun to talk about noise. So we'll see how it goes, okay? Probably every SDR these days has some form of noise blanking and noise reduction algorithms. And the thing is that as our processing power is increasing, we have the opportunity, and we should take advantage of more advanced algorithms to do a better job on these tasks. I'd like to discuss a couple such algorithms this afternoon. And all the algorithms that I'll discuss today are implemented in the WDSP signal processing library that we use for the openHPSDR program. We're going to talk primarily about two types of noise, impulse noise and random noise. Both of these tend to be broadband across the frequency spectrum. The first is addressed with noise blankers, and the second is addressed with noise reduction algorithms. So looking first at impulse noise, if we look at our I and Q waveforms with severe impulse noise, we would see something like this. Our signal and some random noise are here on the center lines, and these spikes are the impulses. And they're caused by things like motors arcing and arcing of power lines across insulators and arcing of spark plugs in cars. Now, a noise blanker, to deal with this impulse noise, has to do two things. It first has to detect the samples that comprise the impulses because they're bad, they've been corrupted. And it then has to replace them with some estimate of the original signal. We have a couple different kinds of noise blankers in the WDSP library, one being wideband blankers and the other being a new spectral noise blanker that we introduced last year. These, let's first talk about the wideband blankers. And there's some variations on this, but typically for detection in a wideband blanker, we look at the power encompassed in each sample, and we compare that power with the average power across some significant piece of bandwidth. There is, however, a fairly well-known problem with wideband blankers, and that is that in the presence of very strong signals on the band, sometimes they fail in detection because they're unable to completely sort out the difference between the strong signals and the impulses based upon power, or even upon edge speed or whatever other technique you want to use. And of course, if we can't detect the bad samples, we can't correct the bad samples. So let's look at our wideband blankers that we have in WDSP. The first one is NB. It's a fairly basic preemptive blanker. Shown here an example. So we have a blue input waveform, just a sine wave, and we have a couple impulses. And then in red, I've shown how it reacts with the output waveform. Now, it uses a short delay line, so we're able to see the impulse before we have to provide the output. So the way it responds is it gradually ramps down the signal, holds it at 0 as our estimate through the impulse, and then ramps it back up afterwards. We also have an interpolating wideband blanker, and it's a little bit smarter. Rather than assuming the signal is 0 during the impulse, it has several modes, but it can do things like interpolate linearly across the impulses. And then we come to our new spectral blanker. This operates quite differently. It does not look at impulse amplitude primarily for detection. It uses something called linear predictive coding. And linear predictive coding says that we can estimate the value of a sample, y, at time m, as a summation of some coefficients, a sub k, that we can calculate, multiplied, respectively, by a set of preceding samples. So we can estimate the next sample. Well, when we can do that, then detection becomes very easy. We just compare our estimate of the next sample with the measured value of the next sample. And if those are very different, we conclude we have a bad sample that needs to be replaced. Also, I should point out that normally an impulse consists of more than one sample. So typically, we don't just find one bad sample at a time, we find a sequence of bad samples that need to be replaced. Correction then, we can again use these coefficients, A sub k. Since we have to replace a sequence of samples, we don't just use the simple formula, we actually write a system of linear equations and solve them for the values of the samples. Since this does not primarily depend upon amplitude for detection, there's a couple interesting properties. One is that it can detect very small impulses smaller than the signal itself. Secondly, it can operate at low bandwidths, can operate at audio rates, which substantially lowers the computational load. Let's look at an example of how this operates. So here again we have a blue input waveform, we have a red output waveform. Outside of the center region, over here and over here, the blue input is directly underneath the red output, so you don't see it. There's no corruption, nothing to be corrected. However, in this center segment, there are a number of small impulses. What happened here is that the detector portion of the algorithm decided that this entire region was corrupt and should be replaced. So what the algorithm then did, it completely threw away the blue input in here. It set it to 0, and it recomputed this red output. Now, it's no surprise that the impulses are gone, but I think it's fairly striking if you look at the difference in the computed red output compared to the original blue input waveform without the impulses. They are almost identical. You can only see a few small deviations between what was computed and what the original waveform consisted of. Have here a real example. This is an IQ file sent to me by Roger, W3SZ. And what we have here is a segment, I think this was 20 meters. We have a very high noise level due to impulse noise. And this was a CW portion of the band that we're looking at. I've zoomed in on that. We have some strong signals. I think there were some stronger than the ones we're looking at. And we also have some weak signals. We're going to listen to the signal in the bandpass there that's circled in green. But before you listen, let's take a look at this in the time domain. And this is, in fact, the picture that I showed you before. We see our impulse spikes. Also, if you look carefully, you can see dits and dahs of a strong CW signal. This was a very strong signal, or you wouldn't be able to see it within a wide bandwidth, a couple hundred kilohertz or 300 kilohertz of bandwidth. But let's take a listen to what Roger heard. And hopefully the sound is going to work for us. Well, maybe not. I may need some help here with the audio.
Das kann sein. Ja doch, geht aber. Also, oder? Ne? Geht? Ja. Wo ist das? Hast du eine Idee?
Das passt schon. Oder ansonsten laut. You can,
Da ist der Lautsprecher.
you should hear something.
So the question at the beginning of the presentation.
Yeah, it's maximum volume. And just go back to the presentation slide 13.
So it asked a question at the beginning. I couldn't see the screen.
It should work now.
Huh?
It should work.
Should work? Let's try it. Let's go back. No, I think it's blocking playing the audio file. Okay, I'll tell you what, let's go out of the presentation and restart it.
Apart from that, you should be able to open.
No, I'll never get through it that way. It'll take me forever.
If it does not work, we do it in the,
Yeah, let's completely shut down the presentation and restart it. Okay. Yeah. Now, I'd asked a question before. There. Now, what does it say?
Ah, okay. Yeah, external content. That's external content, yeah.
Okay.
hopefully we now get
Okay. Can you hear that? Loud enough? Okay, so maybe I'll just play that one more time. So a lot of impulse noise. We can hear the CW signal. We can copy it sometimes, but that's what we have. Now, let's turn on our wideband blanker, but first, let me point something out. You know, we talked about the impact of strong signals in the bandpass on a wideband blanker. What you're going to hear that the wideband blanker will take out most of the impulses. However, there's going to be some remaining, and those are the ones I want you to listen to, because you're going to hear that if you listen carefully, they are clustered like the dits and das of a strong CW signal. So listen to the remaining impulses here. Okay, did you hear that? All right, now let's turn off the wideband blanker and let's turn on our spectral noise blanker. So, so the impulses are gone. What you did hear in the background is random noise, and that's our next topic. Now we have to deal with that. So noise reduction algorithms are used to improve signal-to-noise ratio. But don't depend on noise reduction algorithms to be able to pull out signals that are deeply buried in random noise, because they're looking for the signal and trying to differentiate it from the noise. And if there is no signal-to-noise ratio, improvement times nothing is still nothing, okay? So I want to set your expectations. In WDSP, we have a couple types of noise reduction now. We have our variable leak LMS algorithm. LMS algorithms are very common. They're discussed many places on the internet, many signal processing textbooks, so I'm not going to discuss that here this afternoon. But as of last year, we also have our spectral noise reduction. Now, in this case, by spectral, I mean the processing is done in the frequency domain. So we're going to do an FFT, do some signal processing, and then an inverse FFT. The seminal work for the particular class of algorithm that I'm going to discuss this afternoon was actually published by Ephraim and Malah back in 1984. But there's been substantial improvement in this field over the past 30 years. And in fact, a lot of that right here in Germany. And one paper that I found particularly useful, and by the way, these authors have done quite a bit of excellent work, was the second reference that I gave here, published in 2012. So let's try to understand the problem and what we can do about it in the context of these algorithms. On the left, you see the handsome speaker producing perfect speech, S, okay? That speech goes through the air, to the microphone, through the transmitter, is propagated through the atmosphere. It reaches the antenna, processed through the receiver. At that point, at the output of the receiver, we have an observed signal, Y. It goes through the air and over here to the happy listener, okay? Now, what happens, though, in this process, probably mostly in the propagation portion, is that some random noise, N, is added to the signal. So the observed signal, Y, is equal to the original speech plus some noise, N. We can only observe Y here at the receiver. Our job is to estimate S, the original speech. Now, you know, when you think about that problem, it's not immediately obvious how to address it until you discover something called Bayes' theorem. Bayes' theorem says that we can generate a probability distribution for the probability of a given of a speech S given that we know Y, okay? It's a probability distribution of the amplitude of S given that we know the amplitude of Y. Well, we don't know how to do that until we look at this equation. The probability, according to Bayes' theorem, the probability of S given Y is equal to the probability of Y given S times the probability of S divided by the probability of Y. Well, believe it or not, now we have something we can work with. The probability of Y given S turns out to be just a model of our communication channel. And we know that Y is S plus N. So if we were to use a statistical model, say a Gaussian model of noise amplitudes, and apply that to S, essentially generate a channel model using a statistical model of noise, we can generate, or we can calculate, a probability of Y given S. The probability of S is sometimes called prior information. It is just a statistical model of speech amplitudes. Okay, that's all it is. It's either a Gaussian model or a gamma model. It's a statistical model of speech amplitudes. And it turns out the probability of Y is really just a normalizing factor, and it doesn't depend upon S. So we can generate this statistical model, but we still need to actually estimate S. We can do that. And typically the way it's done is using Bayesian estimation and typically using a minimum mean square error criterion. Now, you don't understand all of this, right? Right, okay. That's what I expected. The truth is, when you actually try to put this into equations, it gets very, very complicated. And that is beyond the scope of our discussion this afternoon. But I can show you a block diagram of the software in a little bit more detail. And this maybe gives you a better feel for what we're doing in this algorithm. So we do our FFT. At that point, we have a bunch of frequency bins. What we want to do is apply a gain to each of those frequency bins. That gain is going to depend upon how much signal and how much noise we estimate that there is within that bin. If we have a high level of signal, we want to apply a high gain. If that bin just contains noise, we want to apply a low gain. And it turns out to figure out those gains, estimating noise power in each bin becomes extremely important. There's a bunch of algorithms for that. I've broken that out as a separate block. But once we've applied the gains, we simply do our inverse FFT, and we're back to our time domain samples. Now, I have a lot of examples here. We don't have time to play all of these. They're sorted by the initial signal-to-noise ratio. We're going to stay in the medium category. And I'm going to first give you an example of what this particular speech sounds like with the spectral noise reduction on. And then I'm going to turn it off so that you can hear what the random noise sounded like before. So first, with it on, You should expect to hear little background noise, a fairly low amount of random noise, and you should expect to hear clear, undistorted speech. So let's see what we have. Okay, could you hear that? Yeah. It's not very loud. I don't know, do we have a way to adjust or? Yeah. Okay. Now let's listen with the noise. Oh, sorry. You hear the difference? Okay. All right. Well, we've talked quite a bit about noise blankers, noise reduction. Often for a given noise situation, the best solution is to use some combination of tools, not just a single tool. And you know, we could talk about that, but I don't know. Phil, you're looking a little jet lagged. You having trouble, staying awake? And I see a couple people in the audience doing this. So what I thought, I was just thinking I'm kind of tired and jet lagged. I thought we might spend the rest of the time just to read a good story. Would that be okay with you? Let's see what we have for today. Doug and the Evil Power Company. This is a great story. You're going to love this story. Yes?
Oh, may I please read it?
Sure, go ahead.
Once upon a time, in a kingdom far, far away called Arkansas, a great noise arose to cover all the signals on all the bands. Doug emailed far and wide. This interference popped up about the same time as the power company replaced the analog meters with digital ones. It's a spread spectrum transmission, ranging from 1 megahertz to 80 megahertz, which appears to be what is known as broadband over power lines, or BPL.
Well, here's what Doug saw in the pan adapter. The noise level is quite high. This is part of 20 meters. Sure enough, all the signals are covered up here. So let's take a listen to what he heard. There is a signal. She's going to get louder. There's a little bit of QSB. There you go. Kilo 7 Bravo. I heard one station respond.
The bands were very noisy, and Doug was very sad. To make matters even worse, this thing was a signal, not just simple noise. This was very bad.
So if we look at the IQ waveforms, I was very curious, so I pulled these out and took a look. They have these regularly spaced big spikes. They're wider than impulse spikes. Very, very strange. It must be some pattern that communicates the information. There's also some other frequencies in here. I don't know if those were part of the original modulation or perhaps some ringing on the power lines. I'm not sure. But it's not clear how to address it.
Fortunately, handsome noise blanking and noise reduction tools soon came to the rescue. Our story has a happy ending. Using a restored in the kingdom, and Dove was happy again.
Well, we've turned on a wideband blanker, our spectral blanker, our spectral noise reduction. Pan adapter looks a lot better. It's down about 25 dB. We're seeing some signals on the band now, so that's encouraging. But the real test is, what does the audio sound like? And even though the voice said that it's a happy ending, I think you're going to have to decide if it's a happy ending. So let's listen to what we hear with those tools turned on. Okay, what do you think? Happy ending? Well, that is, in fact, the end of our story and the end of my presentation. And if time permits, I'll take a couple questions.
A very impressive demonstration of modern digital modes and systems. Thank you very much, Warren. Are there any questions to Warren? Yeah, okay.
Yes, you mentioned LPC as a method for noise reduction, but LPC is also used in the early audio codecs, right? Like GSM, I think? Linear predictive coding?
LPC is very common in audio processing, and I expect that it is. I don't know all the applications, but it's been around for decades. And now we have the computing power to take a lot more advantage of it.
Any more questions? Yeah. Okay, here.
You were talking about the speech model.
Yes.
Is this speech model fixed, or is it in any way adaptive?
It is. The speech model itself is fixed. Obviously, estimation of things like noise amplitudes those are adaptive type algorithms, but the speech model itself is fixed.
Not adapting to the speaker.
It is not adapting to the speaker. There are, however, a lot of different statistical models that people have looked at for speech, and some of the early work used a Gaussian model of speech amplitudes, but it's been later determined that super Gaussian or more heavy-tailed models, such as gamma models, are perhaps better. Yes?
Have you any experience with the noise banking technique used in lean route?
I've talked to Leif about it, and I don't have a lot of personal experience with it, no. He has two noise blankers. I think one he calls a dumb blanker, which is actually pretty smart because it notches out strong signals within the band. Yeah, and then he has...
Yeah.
And then he has another one that must be tuned to the response of the radio. And that one I don't know as much about.
Okay. More questions? Yeah, Marcus?
So could you go back to the slide of the block diagram with the Bayesian estimator for the weights of the bins? Yeah.
This one?
Yeah.
Yeah.
So this is kind of an equalizer, isn't it? It's estimating the SNR and frequency domain and weighting, like the bins that have higher SNR get more power in the end, and the ones with low SNR.
Yeah, that's basically the idea. The algorithm doesn't just look at SNR, it does look at how much signal and how much noise. And in fact, the equations end up being based on two signal-to-noise ratios. One is what we call a priori signal-to-noise ratio, and the other one a posteriori signal-to-noise ratio. The
Backup slides.
Those are the equations.
Cheers. Yeah.
So the gain per bin is a product of two factors, G sub gamma and G sub gamma S. G sub gamma S takes into account something called speech presence uncertainty. If the speaker isn't actually speaking, then we want to behave a little bit differently. And then there's two important things here. These are the signal-to-noise ratios. Signal-to-noise ratios I was talking about. These are very important parameters in calculating those two gains. And in both cases, the denominator is actually the estimated noise power. So those two signal-to-noise ratios are used to calculate the gain.
I have a question back here. Sorry that I just pop in with my question. Well, this is all about statistics. Statistics has a lot of non-integer calculations. This is probably much about float values. So where do you process these values? Do you process them in an FPGA or, I mean, this is all about algorithms, first of all, primarily. So that's the first question. Second question is, if you're introducing these mathematical algorithms to the data, well, signal processing stream, how long do you delay the signal until you can apply all your corrections to the IQ stream?
Okay, so the question about the processing, the entire WDSP library runs on the CPU. John runs it on the the ARM processors. I run it on Intel processors at my place. So it runs on the CPU. I do everything in double precision floating point. For some algorithms, double precision floating point makes a difference, some of these algorithms. In other algorithms, it doesn't. You could do single precision. And in terms of delay, there is some inherent delay. There's a small buffer. It's on the order of a few milliseconds. It's been long enough since I wrote this, I'd have to go back and look at the code to see exactly how much.
So do you think it might be possible to improve upon the algorithm by making use of natural language processing to basically estimate the next likely phoneme?
Yes, there's been work done in that area, and I think it would be possible. You might end up with using a totally different algorithm rather than just changing this one. But this whole field is there's a wealth of research that has been done and could be done, and a lot of it's been motivated by hearing aids, by audio in automobiles, various things like that.
I have another question. Your marvelous work into noise reduction, is it embedded in the openHPSDR program?
Yes, absolutely.
Great. Okay.
Yes.
I'm new to that program, so because of that, my question. Thank you.
Any more questions?
Any comments? Great stuff, I think so, yeah. Okay. Warren, thank you very much for that. May I help you? Yeah. It's very sensitive.